set is infinite if it can be put into one-to-one correspondence with one of its proper subsets. So this definition was described by Herbert Cantor in order to determine the cardinality of infinite sets. He also described the set as countable if it is either finite or if it can be placed in one-to-one correspondence with set of natural counting numbers. The cardinality of any countable set is written this way. This is called Aleph knot. Now, example number one, show that the set of natural numbers is infinite. Just for this hint, what that one means, we have to find a one-to-one correspondence to, for example, this set starting with 2, 2, 3, 4. So one-to-one correspondence. What that one means, we have to find a function that maps our members or elements from one set to another set. So here it's asking to show that this natural numbers, this set is infinite. So starting that part, natural. Here we have to start from 1. Now we want to see how we can map 1 to 2, because using hint, we have to use this set. Now that we have this set is given as 2, 3, 4, it's asking just use this one and compare with natural numbers. But the point is that here we had a set is infinite if it can be put into one-to-one correspondence with one of each proper subset. Now the question is that how we can map this 1 to 2, how we can map 2 to 3, how we can map 3 to 4. What that one means, what we have to do here for 1 to be able to have that equal to 2, obviously we should add 1. So it's 1 plus 1 is 2. So here we have to add 1. We're adding 1, we are able to find this section. I'm going to write what we have to ask, how map 1 to 2. Two to 3. And finally 3 to 4. So we're trying to map and use one-to-one. Instead of writing one-to-one, in words, we can write this way: 1-to-1 correspondence. Starting point here is 1. So I have to add 1 to be able to find the number that we have here in the other set as 2. So our n in the first place was 1. Now our n is 2. So it's 2 plus 1. And we got this one 3. Next one, here n is 3. Again, add 1. So this is 4, which is this number. So based on what we did here on this part, our map is from n, we did n plus 1, because all these numbers that we added 1 to find the other set, all these numbers are n. So here is n plus 1. Since we were able to map this natural number to the other set, that means that this is infinite. Show that the set of even natural numbers, so this one is even, is infinite. So here is hint: find a 1-to-1 correspondence to 4, 6, 8, 10. Exactly same with even natural numbers. So here is, since we have even here, we have 2, 4, 6, 8. So this is what we have for this part. And compare that one with what we have on that part. Sometimes you may not have this set, may not be given. This is just hint. Question will ask you to show that the set of even natural numbers is infinite. And that is proper subset of even natural numbers. How we can map 2 to 4, 4 to 6, 6 to 8, 8 to 10. So here, how we can map by adding 2. That means our function from n, this goes to n plus 2. Since we have this one, this means that this set is infinite, because we were able to find 1-to-1 correspondence. So n is for natural numbers that are used here. And these natural numbers are starting with 2, 4, 6, 8, because we had even. So we've completed that part. But what if was asking to show that the set of odd natural numbers is infinite? So we have to compare that with proper subset. How we can map n to, the answer is exactly the same thing. The next one, show that the set of multiples of 4 is infinite. So writing that way is easier, not writing the first one, starting with a second number, because see, in this case, we have multiples of 4, we have 4, 8, 12. What if this part, this hint wasn't given? Find the one-to-one correspondence to 8, 12, 16, 20. So in this case, you have to find what the next one is. So it's multiply. So 4 is 1 times 4, 2 times 4, 3 times 4, 4 times 4, and the next one is 16 here. So you're going to use these three numbers, 8, 12, 16. Usually what I have here, what is on this part we have three numbers. So to compare the other set, I'm usually using three numbers again. But here, since we have this part, so either one works. Writing 4, 8, 12, 16. You can add more and compare that one with proper subset 8, 12, 16. So this is 4 times 1, 2 times 4, 3 times 4, 4 times 4, 5 times 4. So we multiply natural numbers by 4 to find this set. How we can map this set, multiples of 4, to proper subset. So from 4 to 8, 8 to 12, 12 to 16, 16 to 20, you can say, okay, if I try to subtract and find the difference between, that is 4. So meaning we have to add 4. We can map by adding 4. You only need to write I'm using n for the numbers that are given here on top, multiples of 4. In this case, n is you can use any variable that you want to. You can use m, and that goes to m plus 4. So this is our map for one-to-one correspondence. Now example number 4, show that the set has cardinality aleph naught. What this one means, we have to find one-to-one correspondence with natural numbers. We have to find with natural numbers. So first writing what I have here, natural numbers, and then I'm going to compare this what I have here. I'm going to use 3 dots. And as always, I will use n for natural numbers. Starting with this point, which is 1. Then we have 2, we have 3, we have 4. Now trying to find our function, so how we can map 1 to 1, 2 to 1 over 2, 3 to 1 over 3. So it's just 1 over n. That is 1 over 1, it's 1. So here is our map. So that is said, this one has cardinality aleph naught. That means to find one-to-one correspondence with natural numbers, because it's aleph naught. Since we have 3 numbers here, and again, after that, I'm going to use 3 dots, because comparing that one with natural numbers are infinite. For natural numbers, I will use 1, 2, 3. So 3 numbers. But infinite. So compare this one with what is given. 3 dots. So we have to ask how we can map 1 to 1 over 2, 2 to 1 over 4, 3 to 1 over 6. So I'm going to do exactly the same thing for n. Let's n natural numbers. Starting with n equal to 1. So this is the point that I started. I want to see if am I able to find function to be able to map 1 to 1 over 2. So here is 1 over 2. Here is 1 over 4. Here is 1 over 6. But we have to find a function. In this case, I'm not able to write 1 over 2, 1 over 4. So what is 2? What is 4? What is 6? How we can find a function for this part using natural numbers. So the starting point that was n equal to 1, map that one to 1 over 2. This one, 2 in denominator, means that I can multiply that one by 1. So 2 times 1 is 2. The next one is 2 times 2 is 4. Next one is 2 times 3 is 6. So I just used 2 and multiplied by in denominator. I used 2 and multiplied out by natural numbers. So these are natural numbers, 1, 2, 3. And I use those here in denominator, 1, 2, 3. Meaning that our map is here n to 1 over, because on top for all of these we have 1, So numerator, or what I have on top, all these are same, that is 1, that's why I'm using that one on top. And denominator, based on the numbers that we have here, 2, 4, 6, those are multiples of 2. So it's 2n. So these are multiples of 2. Okay, so this one is 1 times 2, that is 2 times 2, 3 times 2. Next one, we're gonna have 4 times 2, so it's 1/8. So this is our map. So that's set 5, 7, 9, 11, 13 has cardinality aleph naught. So these are odd numbers, odd natural numbers, but we didn't start from 1, instead from 5. So again, we have to find one-to-one correspondence with natural numbers. Since I have 5 numbers here, I'm going to do the same thing. And then 3 dots. Compare that one with these numbers. Okay, first, I'm going to explain this way, and then later having another method to find. What I see here, we're given these are odd numbers. So for odd numbers, I can have, for example, 2n minus 1. Then add 2, I can have 2n plus 1. Again, add 2, 2n plus 3. So all these are odd numbers. You can continue to n plus 5 or 2n minus 3. So all these are odd. If you want, you can try 2n minus 3. I'm not using that one because this you're gonna have negative number, and for natural numbers we have to start from 1. So this is not correct. Mathematically is not correct. So we have to start with 2n minus 1. So n again is natural number. And those starting from 1. So 2n minus 1, that means 2 times 1 minus 1. So this is the starting point, is 1. The z for this part is 1. The next one here we have, so 2 times 1 minus 1 is 1, 2 times 2 minus 1 is 3, 2 times 3 minus 1 is 5. So these are the numbers that we have here. Next one, 2n plus 1. So we have 1 times 2 plus 1. The starting point is 3. So we have 3, 5, 7. Next one here is 2 times 1 plus 3. We have 5 starting point. So it's 5, 7, 9. And also this one, so it's same thing, 2 times 1 plus 5. Now here starting point is 7. Based on what I have here, I can find what our function is. Here we should have 5, 7, 9, 11, 13. The only one that is same numbers is this one, 5, 7, 9, and that was based on what they had here. It's 2n plus 3. So our map is n to 2n plus 3. So this is our map. Now another method, instead of writing all these, writing this again here. So for this part, using what I have for given set, we have 5, 7, 9, 11, 13. I'm going to find what is the difference between the first two numbers. 7 minus 5, the difference here is 2. I'm going to use that one here, multiplied by n, having multiples of 2, so it's 2n. And working on this one, if I use n equal to 1, because for natural numbers, starting point is 1, so 1 times 2 is 2, but I have to add a number to be able to find 5. If not, I'm going to have 2. And this is not 2. The starting step is finding the difference to be able to see what we have here is multiplied by 2, multiplied by 3, multiplied by 4, or whatever. In this case, it's multiples of 2. And then after finding that part, you have to add a number here to be able to map 1 to 5. So 2 times n is 2 times 1 plus another number to be able to have 5, and that is 3. Next one, we can just try the other number, the next one, to make sure that this is correct. So 2 times, now n is 2. So 2 times 2 plus 3, we should have 7. So that is correct. 2 times the third one plus 3. So this is 2 times 3 is 6, plus 3 is 9, which is this one. So this is correct, and that is our map. N to 2n plus 3. Let's have another one here. For example, what if our given set was, instead of 5, 7, 9, was 5, 9, 13, was this one? And we have natural numbers. 1, 2, 3. Find one-to-one correspondence. What is first step? We have 4 times n, x multiples of 4. And add something here to be able to find 5. So it's 4 times 1 plus 1 is 5. Next one here is 4 times 2 plus 1 is 9. The third one here, 4 times 3 plus 1 is 13. So this is what we have for this part. It's n to 4n plus 1.